Welcome back to Applied Mathematics. In this video, we're going to be talking about surface area. I like to think about surface area in terms of what geometers call nets. So if I have a cube, or just any sort of a rectangular prism, really, what I want to do is kind of unfold this cube. So starting at the bottom, fold the right side down, fold the, top side, not the top of the cube, but the upper looking side, looking down on it. Fold that down, fold the bottom down, and then the left side, when you fold it down, the top comes along with it and gets folded down one further. Right? So if you take this shape and you curl it up, you end up with a nice cube. Well, the surface area of an object is the surface of this net, this shape that you can fold up to give you the three-dimensional object that you care about. Right. So for a rectangular prism, if we call these things length, width, and height, well, length is the measurement here, width is the measurement here, and then height will show up there. This will also be the height, and then this will also be the length. Take a couple of minutes staring at that, make sure that that makes sense to you. It might be helpful to literally grab a piece of paper, cut out a shape that looks like this, and curl it up to see how it works. All right. What do I not have measured? I did not mark this dimension, which will be height, and I did not mark this dimension, which will also be the height. But with those markings, each of the 6 pieces here is a rectangle. So we can calculate that as length times width, although we don't really want to use length and width as the names because those are specific things. But the dimension here is length, the dimension there is width. The dimension here is height, the dimension there is width. The dimension here is length, the dimension there is height. And each of those things happens twice. So the area of this shape is 2 times length times width plus 2 times length times height plus 2 times width times height. And it's all being added together, so it doesn't really matter what order we put those things in. A cylinder can be a little bit harder to parse, but if you think about it, a cylinder is formed by just taking a rectangle and rolling it up. Right. Grab a sheet of paper and curl it around itself. You will find that when you curl it up, this dimension becomes the circumference of the circle. And we know that the circumference of a circle is 2 times pi times the radius. This dimension will be the height of the circle, or I'm sorry, the height of the cylinder. And then you will have a perfect circle if you have a closed cylinder at the top and bottom. Well, the area of those things is just going to be pi r squared. So the total surface area of our net is 2 pi r squared, that's this and this. And then this rectangle, which is 2 pi r as its length and h as its width. with a little bit of thought, it becomes pretty clear how to deconstruct this formula. But some of the other shapes we're going to be looking at in a few moments are not quite so straightforward. And so very often, when you look at lists of formulas for three-dimensional objects, you will separately see listed the lateral surface area. The lateral surface area means the sides of the figure and not the top or bottom. We generally use a capital S to represent lateral surface area, and in this case, the lateral surface area is just 2 pi RH, right? Getting rid of that term that came from the top and bottom. The reason that that terminology is so important is because it is much less clear how to deal with a right circular cone. Right, certainly we've got a height, we've got a radius, and then in a lot of sources you will actually see the angular side length of the cone listed as an important part of this. Let's see, our textbook, it looks like, uses the letter S for this. And capital S is going to be pi times r times little s. That'll be the area of the body of the cone. And then the total area would be, well, pi r squared plus pi rs. Although if I change my perspective of this cone, and instead of looking at it from that 3D perspective, if I look at it edge on, you will realize that the thing that they call S is the hypotenuse of a right triangle. So using the Pythagorean theorem, I can get that little s is going to be the square root of r squared plus h squared. So you don't actually need to have that measurement, or put another way, you can figure out that measurement from other measurements and start working with that cone, no problem. And while we're talking about cones, I guess I might as well talk about a frustum of a cone. Remember, I think I mentioned this briefly in an earlier video. A frustum of a cone is a cone where the top has kind of been chopped off. And we will have a smaller radius little r. We will have an outer radius capital R. We will have a perpendicular height. And we will also have that diagonal measurement there. The lateral surface area here is going to be pi times the sum of the big radius and the little radius times s. Little s is a little bit harder to figure out because it's not quite so nice. But if you have little r there and you have big R here, well then to make a right triangle out of it, you need big R minus little r. And you can get that S is going to be the square root of big R minus little r squared plus h squared. But if you can just measure that lateral side, then that's probably easier. And then, of course, the total surface area, well, you've got the lateral side, pi times big R plus little r times S. You've got the circle on the top, pi times little r squared, and you've got the circle on the bottom, pi times big R squared. For the sake of time, I'm not going to go through any applications of surface area, but I think that they tend to be fairly straightforward. If you think about the applications of area in general that we've talked about before, surface area is just area. It's just that we've taken the flat thing and we've wrapped it around. The one new form of application is figure out how much area of stuff you need in order to form this thing in the first place. And then you can look at things like the cost of the sheet material that you're using to wrap into that net. You can look at the mass of it or the weight of it, and so on and so on. But with that, I think this is a good place to wrap up. So as always, thank you for joining me, and I'll see you in the next video.